Hello everyone. I am Madhushekar, a second year BTech student studying in National Institute of Technology Karnataka, Suratkal. And today we are going to talk about a highly fundamental and important noise reduction technique, which is spectral subtraction. In real-world environment, audio signals, especially speech, are always contaminated, whether it be the weather or the fan or any electronical inference. Now, this background noise reduces the communication quality. So, throughout this presentation, we will be talking about how to remove the noise or minimize the noise quality. So, this is done by three main steps, which is signal processing. We process the signal which has the noise in it, by framing and windowing, by creating them as small frames. And the next step is noise estimation. We estimate the noise frequencies in the audio signal. And the third step will be removal of the noise and reconstruction of the signal into speech. So these three steps have subparts which include framing, windowing, short time Fourier transform, noise spectrum estimation, spectral subtraction, IFFT, and overlap add. Now, as I said, spectral subtraction is a very widely used noise reduction technique in signal processing, primarily for enhancing audio signals. This method is essential clearing for clear communication in noisy environment and various audio processing applications. Now, the first step that we do is we convert the audio signal into frequency domain. Now, why do we have to convert it into frequency domain, you might ask? So, the answer to that is noise is a non-uniform across the frequency domain. So, suppose if we remove the noise in the time domain, then we wouldn't have been able to selectively reduce specific frequencies of the noise. So that's why we perform these operations in frequency domain. Now, this approach is really crucial for speech enhancement for hearing aids and as well as for communication devices such as phone or laptops or any walkie-talkies. Yeah. So the main technique that we'll be using to convert it into a frequency domain will be short time Fourier transform, or also known as STFT. Now, as I said, we will be removing the noise from the audio signal. So here, YN is the audio signal or the observed noisy signal, and SN is the clean speech which we want, and the DN is the additive noise which we have to remove from the audio signal. Doing this helps us retain the speech that the audio signal gave. Now, why is this method relevant, first of all? First of all, it's very transparent and explainable. Like, as I explained, we have to subtract the noise from the audio signal. For that, we have to identify the noise domain and we'll have to remove it. After removing the noise, we'll just have to reconstruct the signal. Also, like any other model, this model does not require any dataset or any training, and it's fully explainable through code itself. So coming to the first step, signal processing foundations. Here, first of all, speech is a non-stationary globally, but locally it's stationary. Now, what does stationary even mean? Uh, if if a signal has energy which does not change with time, or a frequency doesn't change, then it's known as stationary. But if it changes or the frequency changes, it's known as non-stationary. And speech is non-stationary. But STFT, it works on only stationary signals. So for this, we perform framing. Now, what is framing? Framing is the process of dividing long speech into short and overlapping segments. These segments are known as frames. So yeah, as I said, we'll have to perform this because FTFT performs on stationary signals only. And here, the frame length, will assume it as n. The hop size is r, which is overlapping of the frames, and the frame index. So extracting the frame equation would be something like this. And typical values of the frame length would be 256 or 512 or 1024. And in this case, we will take the overlapping or the hop size to be 50%, which is n by 2, 50% of the frame length. Now, why do we choose 50%? Here, if there is no overlapping, the amplitude might be discontinuous. So we overlap it to ensure a smooth curve. So that's why we chose 50%, which is ideal. So once the framing is performed, it introduces two discontinuous values. Like the signal will be continuous, but the values will be discontinuous only at the frame boundaries. So that's why we perform windowing to make it as a smooth weighing function. Now, this signal is smoothly tapered along the signal edges. The common windowing techniques would be hamming or hanning, and we will be going through hamming in this video. Now, this is essential because speech spectral estimation is critical for noise reduction, and it is one of the first steps. So any error in this would lead to error in the final result. So here we multiply each frame with a weighing function. Here the weighing function would be Wn and the frame would be Ymn. Now for hamming, the weighing function is as follows: 0.54 minus 0.46 cos 2 pi n divided by capital N minus 1, where capital N is the frame length. Now, as I said, window is necessary because it reduces the side lobes and it gives a better frequency resolution. Now, during this process, the overlapping must satisfy this condition. The weighing function of n minus mr must be a constant. This is necessary for reconstructing the signal. So the fast Fourier transform, or FFT, it converts the time domain into frequency domain signal, and STFT is a part of FFT, which is used for only non-stationary signals. So doing this enables us to view the signal as a time frequency representation. Now, since STFT is converting the time domain into the frequency domain, after performing the framing and weighing, we will get the function as y of n plus mr wn. And converting this signal into a Fourier transform would give us the summation over the frame length uh, with a signal multiplied with e power minus j by j 2 pi k n by capital. Now, since this is a complex wave spectrum, we can write the STFT as the magnitude spectrum into the phase. This phase we'll be using later on, since it's quite difficult to find the phase of the noise and remove it. And also, the phase is not much recognizable by our human ears. So we won't be changing the phase or anything. Now we have the equation, which is the Fourier transform of the audio signal equals to Fourier transform of the speech signal plus the disturbance. Now we find the power of this, that is, we find the magnitude of it, which gives mod y square equals to mod s square plus mod d square plus real times of st. Now, the one assumption we make while during this process is that the speech and noise are not correlated, which gives us expectation of SD equals to 0. So this equation, in this equation, the real part, this 2 real part of SD, it becomes 0 when we take expectation both sides. Thus resulting expectation of mod y square plus expectation of mod s square plus expectation of mod d square. Now we'll go to the noise reduction techniques. So first is the noise spectrum estimation. This involves determining the noise power, and it accurately estimates the frequency of the noise so that it's helpful to reduce the residual noise from the signal. Now here we'll take the expectation of the noise mod d square as phi d, just for simpler representation. And one more assumption that we'll be making in this is that the first m frames, only the first m frames, not only, sorry, the first m frames contains only the noise signal. That is, there is no required signal in the first m frames. So we can take the mean of the first m frames, and that would give the noise power spectrum. Now this spectrum will have a variance of sigma square by m, where sigma is the standard deviation. So as the number of frame increases, the variance decreases. So if the variance becomes lesser and lesser, the noise, the noise estimation is really accurate. But if there are too few less frames, then we cannot estimate the noise properly. So from here we had this equation, the power equation, and we will take the disturbance to the LHS, since we only need the required signal mod s square. So which will give us this equation. So now the previous estimation step, it underestimates the error. So we will have to add a constant alpha, which gives us the equation mod s square equals to mod y square minus alpha mod d square, where mod d square is phi d. This alpha is greater than 1, typically between 1.2 to 2. Now this is required to reduce the residual noise and, as I said, compensate for the underestimation. So now if the noise estimation was perfect, we would have gotten the expectation of mod s square as mod s square. But since there is an underestimation, we'll have to consider this. Thus, it will give a negative bias equation, a over subtraction negative bias equation. So if this alpha is too large, that is really greater than 1, then we can see it affects the signal by a lot, which leads to speech distortion. So thus, the ideal value is only 1.2 to 2. Now, another term is introduced over here, which is musical noise. It refers to a artificial tone caused by a spectral variation during the subtraction. Now, this noise, it degrades the audio quality, which becomes a threat to the spectral subtraction algorithm. So now why this occurs? First of all, after the subtraction, the residual noise, after the subtraction, the noise signal, it gets random isolated peaks and frame to frame uncorrelated. That is, it's not smooth. And why does this happen? Because noise estimate is constant across frames. That is, the mean value is a constant value. But the noise itself fluctuates randomly. This can cause spectral spikes or tonal artifacts. So statistically speaking, variance of residual noise increases. That is, the accuracy decreases in low energy regions. So this musical noise is one of the drawbacks in this process. Now, reconstruction of the subtracted signal using inverse fast Fourier transform and overlap add. Now, this overlap add, it combines individual frames smoothly, reconstructing a continuous artifact reduced output signal. So as I said, the musical noise is a drawback, and this overlap add is a technique to counter the drawback, counter the musical noise. Now this overlap, we can say it's kind of similar to the weighing function or the weighing method. So here, we'll combine the magnitude that we found by subtracting the noise, and the phase will be using the noisy phase itself. And as I said, it's because human ears are like really less sensitive to the phase. So finding the inverse Fourier transform of this, we will get 1 by n summation of the frame length n as of the signal e power j 2 pi kn by capital E. And reconstructing this would give us this equation Sn minus m. Now note, while framing, it was n plus mr. So while reconstructing it, it will become n minus mr. And it must also satisfy this given equation for the perfect reconstruction. So the algorithm that we followed now, it consisted of framing, windowing, FFT, noise estimation, spectral subtraction, IFFT, and overlap adding steps, and as well as reconstruction of the signal. Each step must be optimized for accuracy and computational efficiency to achieve high quality noise reduction. So now spectral subtraction complexity depends on the FFT size, frame shift, and the noise estimation method. Here, it was the Hamming method. Uh, Now, this offers a real-time capability with modern processing power, balancing the effectiveness and the computational efficiency in practical applications. This method is efficient enough for digital signal processing and few embedded systems. So from here, we can conclude that spectral subtraction remains a foundational reduction technique since it's simple and really well explainable. Now, as I said, challenges like musical noise requires ongoing refinement, which we counted through the overlap add. But but even with the musical noise, its adaptability and effectiveness sustains its use in diverse audio applications. Now, what are the strengths and weaknesses of this method? The strengths are it's simple, as we just saw. Low computational cost. It requires a really low cost. Works well with stationary noise. And it has a good baseline or it creates a good foundation. And the limitations of this is this STFT, it works only on stationary. So it fails with non-stationary noise. And musical noise is introduced. It is sensitive to noise estimation. So if the noise estimation is bad, then the processed signal will also be really bad. And the speech, and as we saw, if the alpha is too large, it gives a speech distortion. So that's about the explaining part. Now we'll take a look at uh, the process. Now I've coded the spectral subtraction using Python, using Google Colab, which can be browsed. So here we'll be loading the file using libzosa, and this will give the sampling rate and the signal length. Now, as we saw, we need the parameters and we'll define them. Frame size, which is the frame length or capital N, we'll take it as 1024. Hop size, which is the overlapping, we'll take it as 550. Alpha, we wanted it to be between 1.2 to 2. So we'll take it 1.5. And the windowing method will be Hamming, as I said. And here, using STFT, we will find the magnitude and the phase. This phase will be using later on, well, reconstruction. So as I said, we'll have to assume the first M frames to be N frames to contain noise only. So here, the noise samples, it will be the sampling rate, SR, into the number of seconds that you need. So this will find the mean of the noise only in the first 1 second. Now, if we wanted to find the mean of only 2 seconds, then we had to give 2, or the first half second, we had to give 0.5. In this case, we'll take it as 1 second. Here we'll be calculating the noise magnitude. So here the phase won't be needed since we'll be working with magnitude. And this is the spectral subtraction. And the clean signal, we'll use the clean shift. And the phase will be using the noise phase itself. So, and now we are saving the file. And after saving the file, we plotted the original spectrum, which I'll be showing the noise, and the denoised spectrum. So, yeah. Now I will run the code. Give it some time. So yes, I have saved the noise and the processed signal or the denoised spectrum in. I just stop 1 second. Yeah. So the noisy speech would be something like this. So that was the noisy speech. Whereas the denoised output would be something like this. Now, as we can see, the difference was quite a lot. And then the slight background music, I mean, background sound, the denoised spectrum, it was because of the musical noise. So that was about it for this video. Thank you.